we know that if there is a body, imagine this body in space. If it has got a mass and if it is applied to the force F, the acceleration that it gets is A, and the relation for this three terms is F is equal to ma. We have been using the same thing for a vehicle with wheels. Instead of this force being applied outwards, so it is applied through a torque here, T, and that actually provides a forward force. We know that the torque is nothing but the tractive force into radius. So you can actually find out this Ft, which is the tractive force, which is actually divided by the torque at the wheels divided by the radius of the wheel. Okay? We thought that this equation would be right. Now, at this point, I will tell you that this equation is almost 80% right, but we have not actually considered one point because we forgot one thing. You tell me now, in a vehicle which is moving, imagine that the vehicle weight is 1000 kgs. The vehicle weight is 1000 kgs. Imagine that this vehicle is being pushed on a slide, no wheels, nothing, no engine, nothing. It is being applied with a force from behind, some way, and it is on a frictionless surface. Mu is equal to 0, no air drag, nothing. No air drag, nothing. Then we can use this equation. F is equal to ma, this equation is definitely okay. But now, what we are trying to do is that we are trying to see that if there is a tractive force which is applied at the wheels, that tractive force accelerates the vehicle body linearly, and also it says that there are some parts here which is the engine, which is the clutch, which is the gearbox, which is the drive, then the differential. There are some parts and the wheels, the front wheels and the rear wheels, totally 4 wheels. Along with this vehicle getting linear acceleration, these parts are also getting angular acceleration. They are not just sliding and going forward, they are also trying to increase their angular velocity. So therefore, we could make a small mistake. Of course, the error is not huge, error could be around 20 to 25%, but we could make that error. Suppose if you are an engineer who would go to the field of vehicle dynamics, you should know this concept that acceleration of a vehicle cannot be just with this formula, because the parts of the vehicle are not just having linear acceleration, they are also having angular acceleration. Linear acceleration is this, angular acceleration is this. So there are a lot of parts which would now increase their angular velocity. Now to increase that angular velocity, you need some torque. That torque is lost at the wheel. Whatever the torque that was available at the wheel is lost because those parts would actually take away some part of the torque while accelerating. So for now to build that concept, let us actually take an example of a fan which is being run. Now let me actually switch off this one of the fan here. I don't know which I can switch it off first. Okay. Nice. Okay. I don't know which. Okay. Which that stops as early as possible. Now guys, we want to estimate the power which is supplied to the fan. Any guess what is the power consumed by the fan?
30
Guys, any guess what is the power consumed by the fan?
30.
Please find out in your phone. It would be surprised why is this guy searching all this. Okay, you find out the power consumed by your fan. The phone search ಮಾಡಿ phone ಸ್ವಲ್ಪ confuse ಆಗಿದೆ.
75.
Huh?
75 watts.
75 watts. So your fan, the power consumed by the fan is 75 watts. 75 watts is almost 0.1 bhp. Of course, this is the maximum power that the fan can consume, but at lower speeds like 1 speed it may start with 35 watts, At higher speeds, it may actually, you know that there is a knob which actually changes the input voltage or current. So right now I'm confused whether it actually controls by the current or voltage. Okay. Now, with the various knob positions, it may take different power. It may actually consume different power. Now imagine that I have actually put this fan into full top speed 5 and actually turn this on. Now it is at 0, so that is at 0 seconds, it is 0 RPS. At 0 second it is 0 RPS. Now I am turning this on. I don't know which to turn. Okay. Okay, now let us see now. How many seconds it took to gain 1 RPS?
1.5.
Last time we saw this very clearly because I had actually told what is 1 RPS. 1 RPS means the same fan blade should come again to the same position after 1 second. It almost took around 3 seconds. It almost took around 3 seconds to gain that speed. Not instantly when I put it, after 1 second it did not actually gain that speed. So after 3 seconds, it actually gained 1 RPS. 1 RPS. These are basic physics without which you may solve a differential equation, but you don't know if there's basic equations, basic things to handle. You may not be able to handle higher level of problems in the real engineering world. So I'm trying to give a very raw example here. Okay. Now we know that for a fan there are 3 blades like this. Now if I actually apply a torque T here, very similar to this F is equal to ma, can you write an equation which is actually relating to torque and some other terms? You have the equation F is equal to ma. For a rotating body, what is the equivalent equation? What is the equivalent acceleration? Huh? Okay, instead of linear acceleration, it is angular acceleration alpha. Instead of mass, moment of inertia. Moment of inertia I is nothing but mk square. Mk square, where mass of all the 3 blades, where all the mass of all the 3 blades m1, m2, m3, all the 3 blades can be placed in an imaginary plane as a ring. Imagine that all these 3 blades is actually converted into a single ring and it gives the same inertia for rotation. So that means if I try to rotate this, it feels that the same fan is being rotated. Okay. So if you can actually put the same mass into the same single ring at some position, that R is called as K. So K is called as the radius of gyration, which is an imaginary radius at which this mass can be put and you feel the same resistance to rotation. Okay. What do you think is the weight of this single blade? 1 kg? Less than 1 kg? After
200 to 300.
so one blade will be less than 1 kg? 500 grams? So let us actually take the whole blade and this hub, everything to be around 2 kgs. 2 kgs. So let us say that mass of this is actually 2 kgs. Now what do you think is the radius of gyration? In this span, you need to put all this mass not to the periphery, not to the center, somewhere here. So it is not even half, it is slightly less than half. What do you think is the distance from the center to this radius? I mean this periphery of the blade.
50 cm.
Is it actually slightly more than half meter? I think it's slightly more than half meter. It is 600 meters. So you can almost take it as 250. The radius of gyration, you can take it as 250 mm, which is actually 0.25 meters. So let us say that K is actually 0.25 meters. Okay. Radius is actually 0.25 meters. Now, let us work with these equations here. The torque which was produced by the fan is I alpha. I alpha is mk square into alpha. What is alpha, guys? Basically, linear acceleration is change in velocity divided by time. So this is change in angular velocity divided by time. So change in angular velocity divided by time is final angular velocity minus initial angular velocity divided by time. Okay. Now T is equal to m, which is actually 2 kgs, multiplied by k, which is actually 0.25 meters, multiplied by omega final. Omega final is 2 pi n divided by 60 divided by 3 seconds. So omega final is 2 pi n, which is actually 1 rps. After this 3, this is 1 rps. So this is 0 divided by 3 seconds. One round per second. One round per second. Now guys, now can somebody give these values now? Guys, somebody please use the calculator. Two into 0.25. Here second cancels out. 0.262. So let us look at the units here. Guys, this per second is not cancelling out because this is the denominator. It goes here. It becomes second square. What you have is meter per kg meter per second square. Kg meter per second square. What is this kg meter per second square? Sorry, it is actually meter square. So kg meter square per second square. So which you can write it as Newton meter. So this is 0.262 Newton meter. Guys, you just got the torque, but I wanted power. You said 75 watts, no? Let us check whether our basic fundamental equations are at least close to that value. Suppose if I put it to fifth speed, you said 75 watts of power that it consumed. Let us say that by the equation P is equal to 2 pi nt, let us substitute this value P is equal to 2 pi nt by 60. So let us see, so 2 into pi, so 3.14 into n. N we have actually taken it as 1 round per second. 1 round per second divided by 60 seconds. And the torque that we got was 0.262 Newton meter. Zero point 0.0274. So units, let us look at the units here. So this is Newton meters per second square. per second square. Is this the value of power? Newton meter per second was watt. So we have gone torque. Watt per second. I have done something wrong somewhere. Okay, guys, I have done some mistake here because we divide by 60 seconds if it is an RPM. So we don't need to divide this by 60 seconds because it is already in RPS. So the 60 second is not there. So what you will have is Newton meter per second multiplied by 0.60. Sorry, 60. How much? 1.64? 1.645 Newton meter per second, which is watts. Guys, this is value, right? Guys, we got a really different answer. We expected it to be around 25 to 30, but we have got the value of the power as 1.4 watts, which is a very low value. Maybe that is consuming a very low value because maybe the seconds that we took was wrong. If you can actually make it proper with the weights and the radius of gyration, everything proper, definitely would have guessed the power of the fan.
We are not running it in full speed now, sir.
Yeah. Maybe for that reason the watts consumed is very less. And also we might have done some error in calculating the angular acceleration. In this way, you can definitely guess the power consumed by a fan.